Hey, welcome! Today, we're gonna crack the code on a concept that's literally everywhere, from how a meme blows up online to how your savings account, hopefully, gets bigger. We're talking about geometric sequences, and if you really want to get a feel for exponential growth, you are in the exact right place. Let's jump in! All right, here's our roadmap. First, we'll figure out the basic pattern. Then, I'll give you the one single formula you'll need to solve pretty much anything. After that, we'll run through some examples, I'll show you a couple of common traps to avoid, and finally, we'll see how all this stuff actually shows up in the real world. Okay, so let's start with what you probably already know. You've definitely seen patterns where you just add the same number over and over again, right? Well, today we're going to level up from adding and switch over to multiplying. So, seriously, what on earth could a viral cat video and your bank account possibly share? I know, it sounds like a weird riddle, but the answer is this really powerful idea in math: geometric growth. Let's put these two side by side. You've got your arithmetic sequences where you're just adding a number, let's say 2, over and over. But with geometric sequences, and that's our focus today, we are multiplying. It seems like a tiny change in rules, but believe me, the results are explosive. So here's the official lingo. A geometric sequence is just a list of numbers where you get the next term by multiplying the one before it by some constant value. And that special multiplier, we call it the common ratio, and we just use the letter R for short. Now that we know what we're working at, you need a tool to actually work with these things. And luckily, there's this one awesome formula that's basically your master key for any geometric sequence problem. And here it is. This formula is your absolute best friend. I know, it might look a little intense with all the letters and numbers, but it's so powerful. This little thing lets you find any term in a sequence without having to multiply over and over and over again. So let's break down what each piece actually means. So let's go piece by piece. A sub n is just the term you're trying to find, like the 10th term or the 50th term. A sub 1 is easy. It's just the very first number in the list. R is our common ratio, the number we keep multiplying by. And n is just the position of the term you want, like 5th, 8th, 20th, whatever. Okay, enough talk, right? Theory is great, but let's actually see this thing in action. We're going to walk through a few examples so you can really get the hang of using this formula. All right, problem number 1. We've got the sequence 2, 6, 18, 54, and it just keeps going. You can tell right away the numbers are getting bigger, so our common ratio is definitely going to be more than 1. Our mission? Find the 8th term in this list. So here's how we do it. First, what's our starting term? A sub 1. It's 2. Now, for the ratio R, just divide any term by the one before it. So 6 divided by 2 is 3. Perfect. Now we plug it all into the formula. We want the 8th term, so n is 8. That means our exponent is 8 minus 1, which is 7. So we've got 2 times 3 to the 7th power, and that gives us a whopping 4,374. Let's try another one. This time, the sequence is 100, 50, 25. See how the numbers are getting smaller? This is what we call a decay sequence. But don't let that throw you off. The process is exactly the same. The secret, again, is the common ratio. Just do 50 divided by 100, and you get 0.5, or 1/2. Because our R value is less than 1, the sequence shrinks instead of grows. This is the math behind all sorts of things, like how a bouncing ball loses height or how medicine fades in your system. Let's use the exact same steps. Our first term is 100. Our common ratio is 0.5. We're looking for the 5th term, so n is 5. We plug it in, that gives us 100 times 0.5 to the power of 4. Punch that into a calculator, and you get 6.25. See? Same formula, works every time. All right, you ready for a bit of a puzzle? This one's a little trickier. We don't have the first term. All we know is that the 3rd term is 12 and the 6th term is 96, and the job is to figure out the common ratio R. Here's how you think about this. To get from the 3rd term to the 6th term, how many times did we have to multiply by R? Well, from 3 to 4 is once, 4 to 5 is twice, 5 to 6 is 3 times. So we multiplied by R 3 times. That means 12 times R cubed equals 96. Now it's just algebra. Divide 96 by 12, which gives you 8, so R cubed is 8. And what number times itself 3 times is 8? It's 2. So our common ratio has to be 2. Okay, now that you've seen how to do it right, let's talk for a second about a couple of super common traps that are really easy to fall into. If you can avoid these two, you'll be in great shape. This is, without a doubt, the number one mistake people make. It is so tempting to just use n as the exponent, but it's always n minus 1. Always. Just think about it. To get to the second term, you only multiply once. To get to the third term, you multiply twice. You always make one less jump than the term number you're trying to find. So remember, n minus 1. The other big mistake is just mixing up your patterns. You get so focused on one type, you forget the other exists. So the very first thing you should do when you see a sequence problem is ask, am I adding the same number or am I multiplying? If you're adding, it's arithmetic. If you're multiplying, it's geometric. That one simple check will save you so much trouble. So the big question, why are we even learning this? Does it ever come up outside of a math class? And the answer is a huge yes. Geometric sequences are all around you. So let's look at maybe the most important real-world example there is, compound interest. Compound interest is basically the engine of growing wealth. So imagine you invest $1,000 with a 5% annual interest rate. Your starting term, A sub 1, is that $1,000. Now what's R? It's 1.05. And why? Because each year you keep 100% of your money. Plus, you get another 5%. So you're multiplying by 105%, or 1.05. Let's find out what that $1,000 becomes in 10 years. We just plug everything into our trusty formula. We want the value at the start of year 10. That means it has grown for 9 full years, right? That's our n minus 1. So we have 1,000 times 1.05 to the power of 9. And what do we get? About $1,551. That's over $500 that you did absolutely nothing to earn. It just grew on its own. That is the incredible power of geometric growth. You're not just earning interest on your initial 1,000, you're earning interest on your interest. So there you have it. You know what a geometric sequence is, you've mastered the formula, you've seen the common mistakes, and you've seen how it can actually make you money. So now that you see the pattern, my question for you is, where else do you see this kind of exponential growth or decay happening in the world around you? Think about it. Thanks for watching.